independent. And so we have f of x equals to e to the power of x cosine x, and g is our second function, which is e raised to the power of x times sine x, right? So we're tasked with determining if these functions are linearly independent. And we know that functions are linearly independent when they can't be written as a combination of, each other. So the two given equations here. And so in other words,
Hold on a second. Okay.
yes.
Okay. Yeah, explain what you mean.
Yes,
Yeah.
in other words, in terms of, differential equations, we know that two functions on an open interval I are said to be linearly independent on I, that interval, provided that neither is a non-zero constant multiple of each other or the other. And so if two of the functions are not linearly independent, then you know that they're linearly dependent, right? So that's the context that we're given from this class.
Okay. So right. So easy way to remember if two functions are not independent, not linearly independent or linearly dependent, is you cannot represent one with the other.
Right.
It's an easy way
So
to, right? Okay.
exactly.
That's
So
an easy
they
way to.
one
If they
one way
Yeah, if they are linearly dependent, you can always write one in terms of the other.
exactly, like using scalar multiples is a great
Yes.
example of showing that they are linearly dependent. Okay?
Okay,
So
good.
here we're given these two functions, f of x and g of x, and we're going to go ahead and check if these guys are linearly independent. And the method that we use to check if these functions are linearly independent is by calculating um, the determinant of a 2 by 2 matrix. And in our class, we call it like a Wronskian, I think. And
Yes.
so it's the same way that you do it in linear algebra with a 2 by 2 matrix. So you have, entries A, B, C, and D. Or in our case, we'll have like KG for like representing f of x, and then we have g representing g, and then the derivative of both of those functions, kg and g. And so I'll be referring to both, like the linear algebra context and the differential equations context. And so I'll use, both of those notations here. And so we're going to want to find the derivative of f of x or kg and the derivative of g being g prime, right? And f prime would be the derivative of f of x. And so given that our function f of x is equal to ex times cosine x, if we want to find the derivative, we're going to use the product rule. And then here is our derivative. And the same thing for g of x, and here's our derivative. So then we can set up our matrix, first entry at like position 1 in row 1, column 1 is A, and then going on is A, B, C, D. And then in differential equations, we're going to refer, to f of x as kg, and then the derivative would be c, and then g would be b, and then g prime would be d. I hope this is clear. Like, they're side by side. And then you're going to take the determinant of this 2 by 2 matrix. So it's the same thing. You're going to do A
Sorry,
times D.
sorry,
Yes,
Gregory.
ma'am. Yes,
Why
ma'am.
is the kg? Why is the kg prime?
Kg, I just explained kg would be f, and then kg prime would be the derivative of that. But here, in this context, we're saying that this is the determinant.
No, because your Wronskian is over f and g. So why don't you use f prime? You wrote as kg.
That's just how I saw it in, the notes. So just referring to it, but I'm actually doing it this way. I'm just using, the terms that we have from the notes. But I'm
But
actually doing it the way on the left. But it's the same
okay,
thing.
so but no, it's not the same thing. If you
Oh,
write f equals to the kg, that's a big problem. That tells you
right.
already those two are linearly dependent. If you
Right.
F
Okay.
equals
So when I was
G,
referring to the notes, sorry about that. I understand. Yeah, this is a scalar. Um, but what we're supposed to be doing is finding out when they are not um, dependent, right? So
right?
this matrix is wrong. I got it.
Okay,
So this would be, something else, not in terms of G. Okay.
right. Just F prime.
Right.
Okay.
Okay. Perfect. Um, so if we continue along, now that that's rectified, we set up the matrix following this way, right? Um, A would be f of x, B would be g of x, C would be the derivative of A, and then D would be the derivative of B, right? And so we have to check the determinant and see if it's not zero. If the determinant is zero, that means they are dependent. And so let's get rid of this while we're here, so we don't ever look at that again. Perfect, right? So
That's
if we go ahead, sorry?
zero. You have KGG
Yeah,
prime
yeah, yeah,
minus.
yeah. Sorry about that. I was a bit sleepy when I was doing this one. Okay. Um, anyways, if we do the multiplication of this term times this term, we're going to go ahead and get this great mess. E to the power of x times cosine x, which is this first term, a, and then times d would be e to the x sine x plus e to the x cosine x, right? So this would be ad here, the first term of the determinant. And then you're going to subtract that from the C term and the B term, which are multiplied by each other. And you're going to subtract the AD from the BC, and here we have e to the x sine x, and then e to the x cosine x minus e to the x sine x. And then if we go ahead and just distribute this negative sign on these terms here, right, since you're doing a multiplication first and then subtracting them, we're going to go ahead and see that when you distribute the negative sign, you have this term repeat, e to the x cosine x times e to the x sine x on, this side and this side. And so if you add them together, adding the same thing with the negative same thing, you're going to get 0. So these terms are going to cancel out and we'll be left with a positive e to the x cosine x times e to the x cosine x and e to the x sine x times e to the x sine x. And since these are not the same term, um, this will then show us that the determinant is not 0, as this would be the result of the determinant. And since it's not 0, these two functions are linearly independent. Back
Great,
here, e to the
great.
x times cosine x and e to the x sine x.
Yeah, but
Thank you.
Gregory, I would suggest you not introduce A, B, C, D
Uh,
into this. Because Wronskian just between F, G, and F prime and G prime. It's so easy. You just remember Wronskian of F and G equals the
oh,
determinant of, you don't even have to remember the determinant of the matrix. Just
uh-huh.
think F G prime minus F prime G. It's much
Oh,
easier. You don't need to introduce A, B, C, D, use A, B, C, D. Because
oh,
you're going to be confused out of so
oh
many
no.
variables. Yeah.
Really?
Because
I found it easier this way.
are you find it easier? Because
Yes, of
Wronskian has,
course.
oh, okay. All right. If you think if it's good for you, yeah, go ahead. All
Yes, yeah,
right.
I just remember it a lot from linear algebra. You do these all the
Okay.
time.
Okay. All right.
Okay,
Okay.
thank you. I
Eh,
hope no one here is confused. I'm also doing questions 2 from homework 7, just for Kate, since she just asked. Okay,
okay. Thank you.
thank you.
So,
Mm-hmm.
so Liz, are you ready? Not yet. Okay, let's go with Shu Xian. Shu Xian. Shu Xian has her own question. Okay, let's skip the calculation part. All right, because this is supposed to be a little bit advanced course. So let's skip the calculation part. We don't have to read the calculations. Shuxian, are you ready? Well, let's go with David. David also from Home 7. And she, yes, you can go last. No problem. I know you have to travel.
Okay, so I'm doing problem number 6, where the question is to find the general solution to the differential equation. Here it's y double prime minus 8y prime plus 16y equals 0. The standard approach for this type of problem is that we're going to let y equal e to the rx, y prime equal...
Hold on a second, David.
Yes?
This one is being presented already.
Has it?
Yeah, I don't want to see this kind of anymore.
Oh, really? Okay.
Yeah.
Should I just...
We have presented enough. Just prepare for next class then. If you have a homework from 7, this is from 6, right?
Yeah.
Yeah, no more 6, 7 or 8. Okay, thank you though. Let's see, anybody else from 7? Okay, Su Xian, ready? Go ahead. If you're ready, go ahead, Su Xian. Su Xian, lower your hand. Otherwise, it's going to be here forever. Okay, then Yaprak, you can go after Su Xian. Okay, again for calculation, let's skip the calculation. Okay, just explain. Okay, just explain. You don't need to read. Su Xian, your work showed up, but now disappeared. Okay, maybe Su Xian, maybe we'll let Yaprak go first. You get yourself ready. Okay, Yaprak, you can go first.
Okay, so my question is, prove that y sub 1 of t equals 1 minus t and y sub 2 of t equals t cubed cannot both be solutions to a differential equation y double prime plus p of t times y plus q of t equals 0 for p of t and q of t continuous on the interval -1 from 5. Okay, so first I computed Wronski, and then later on we checked if it's identically 0. It's 0 when t is 0, but for the endpoints -1 and 5, we see that it's not. So we can conclude that these two are not solutions. And it also implies that...
Hold on a second, I'm sorry. So what do you use Wronski for?
To check if it's identically 0 at the endpoints, and to see if it's solutions or not.
Because Wronski is for you to check if two functions are linearly independent, right?
Yeah.
So, but you're saying you're checking something else.
Well,
can you explain to me how you use it?
Because like I read the lecture notes and I see a part where it was like, if it's not equal to 0, it's like they're not solutions to the differential equation. If I'm like, did I understand wrong?
Right. Okay, if you check one of them to be solutions, you could just calculate y prime. This is just y double prime and the y.
Yeah.
Okay.
Mm-hmm.
You could just plug in the value to it to check if it's to see equals 0, right? Because if Wronski equals 0, that means those two functions not
Are
linearly
dependent.
independent.
Yeah, they're dependent.
Right. They only check that, but they won't be able to tell you if there are solutions to the differential equation.
If it's linearly independent, it's
Right.
not a solution, isn't it?
Well, they have to be linearly independent to be a solution. Oh, okay, I see your point now. Okay, I see your point.
Oh,
So basically, you assume there are solutions to the equation already.
I mean, because like it says, prove that they're not a solution to this differential equation. So
right.
that's why.
Cannot
Yeah,
both
so
be.
solutions. Yeah.
That means it could be one of them is not, or maybe two are linearly dependent.
Yeah,
Okay.
but it turns out they're linearly independent because
okay,
the Wronski is not 0. And
okay,
then,
I think I know your approach now. Okay, go ahead. Keep going.
And actually, this was the end of the question, but then I added another part. So I tried to find the functions like P of t and Q of t that satisfies that these two can be like solutions to this differential equation. So here I calculated the first and second derivatives of these two functions, y sub 1 and y sub 2. And then I just solved for like P of t and Q of t at the end.
Okay.
Yeah.
What do you mean solve P of t Q? Oh, okay, I see. The P of t of this, the P of t and the Q of t are those two.
Yeah, you said we shouldn't like explain the calculations, so that's why I just say it shortly.
No, I don't want to read. Right, I don't want to.
Yeah, so that's why I just said I solve for P of t and Q of t to find those functions.
Yeah. Okay. Just one more time. Just from the very beginning, explain to us what you did. Very nice question.
Okay. So the first part of the question was asking to prove that y sub 1 and y sub 2, why like these two cannot be solutions to the given differential equation. So if like I computed the Wronski to see that it is not equal to 0, because like if it's not equal to 0, it means they're not dependent, so they're not solution to this differential equation. So that was the first part, and then the second part was to
hold on a second. Hold on a second. Let me see my notes.
Okay.
Yeah. Because Wronski only tells you if two are linearly independent or not. But yes, let me see.
I have a question, Professor.
Yes, go ahead.
Oh, okay. So what are we looking for again? I think I just did a question based on the Wronskian, right? I just wondered what we're looking for.
Right. Her question. Okay. Yaprak, can you explain your question again to Gregory?
Yeah, I would love to understand. So, what the professor looks for the answer.
Okay. So the question is asking to prove that y1 and y2 cannot both be solution to a differential equation, which is y double prime plus p of t times y plus q of t equals 0. So my thought was that if I can show Wronski is equal to 0, because like it literally means they're not linearly independent functions. So, and which means you can't write in terms of y1 and y2, right? So we can conclude that they're not both solutions. But if it was equal to 0, it would mean that these two are linearly dependent, so that you can use those to write the differential equation?
All right, I think that's a great question. I honestly don't know the answer. That's why I just wanted to hear the question again, because I wasn't sure if I was understanding correctly. But I guess I'll wait for the answer.
Yeah.
Hold on a second. I'm just checking my notes to see which part. Can you show me anywhere you found it in my notes?
Yeah, sure. So let me stop sharing. Okay, so
Are you trying to apply this theorem?
yeah, that's what I was doing.
Okay, let's read the theorem. The theorem says if y1 and y2 are two solutions of homogeneous second-order linear equation, which you have on an interval, on an open interval, on which p and q are continuous. So saying if y1, y2 are linearly independent, then the Wronskian equals 0 on the interval. If y1, y2 are linearly independent, then Wronskian not equal to 0 at each point. So you are doing the control positive. So the question was asking you to disprove y1, y2 are both solutions to that, right? So you're saying, okay, I'm going to use a Wronskian. So Wronskian, you calculated, you don't get 0, which is not equal to 0, right?
Yeah.
Well, that tells you, so by B says if y1, y2 are linearly independent, then Wronskian not equal to 0. So you are saying because Wronskian of those two, y1, y2 not equal to 0, so they cannot be the solutions to the second order differential equation.
Yeah, because you can't use them to write the differential equation. So yeah.
I don't understand that. I don't think that's a concrete argument. Because sometimes, because if only goes one way, if then only goes one way. If I use if and only if, that goes both ways. If and only if, that goes both ways. You're trying to use the other way. No, it wouldn't work.
Oh, okay.
Okay, so
the question is not true. I mean, like my solution is not true.
Your solution, can you bring back again? That's the question.
Yeah. Oh.
That's which homework? Homework, which one? 7 point.
It's based on 7, but I just find like online, and then I try to do on my own.
Oh, you made up yourself. I see.
Mm-hmm.
Right. That's why, to me, to my eyes, it looks strange because I would, yeah.
It's loading.
What I would do is no, it's okay. It's good. It's good. So what I would do to the question itself, I would do like this. I would first check to see if y1 independently, right? I would check to see if y1 can be a solution and y2 can be a solution. Like just go directly. I wouldn't use then the second part is this. Okay, actually this is a good question. Think about it. I like this question. Okay, let's see why this is good. Because this involves a lot of thinking. So first I would check to see if y1 is a solution and y2 is also a solution. So remember in the very beginning of 7 says if y1 is a solution and y2 is also a solution to that, there exists a C1, C2, C1y1 plus C2y2 will be a solution also. Remember that? Yeah. So you could use, so you use Wronskian to see Okay, for that to happen, y1 and y2 has to be linearly independent. So here you already checked. So the Wronski of y1 and y2 are not equal to 0. That means those two are linearly independent. If they're both, right, linearly independent, that means C1 of y1 plus C2 y2 should be, could be, not should be, could be a solution to the second order equation. But then you directly check. You check to see if y1 is a solution, y2 is a solution. I bet one of them is not a solution.
Okay.
Then you can arrive this, arrive the end of it. Okay, all right. It's good. It's always good to, but try again. Maybe bring up next time. So.
Okay.
Okay. All right.
Thank you so
Good
much.
try. Oh, you're welcome. Thank you. Okay, Su Xian, go ahead.
Professor, can you hear me now?
Yes, I can hear you.
Okay,
Can bring up
because I change different device and then this one's good. Okay, let me see.
Okay.
Download. Download image 11. Oh, I don't know why. So I did it, but can't work. So let me see. I open it.
Liz, are you ready? Oh, yes, it's up.
Oh, okay.
It's up.
Okay, thank you, Professor. So, the questions from 7 is find a particular solution to the initial value problems.
Su Xian, no
Yeah.
more.
No more?
No more from
Okay.
6. We have presented enough.
No, that's 7.
That's from 7? No,
Yeah.
I don't want this anymore. Okay, I don't want this anymore. We have presented last class enough. Thank you very much.
Okay, sure. Thanks.
Okay. Liz, are you going to present something similar? Do you have any question? David, question?
Yeah, I just wanted to know, does this mean we have to consistently prepare questions that are a chapter ahead of what we're doing?
Yes, yes. Because some questions, if we have presented enough, there's no point of it. Because the presentation serves as a review, a learning
Okay.
time.
So we have to learn ourselves, basically, and then
You don't have to. You don't have to. You don't have to. So probably we're going to, some of the students are going too fast.
yeah, I mean, I could. I mean, I just
Yeah.
prefer to learn it first, and then.
I understand, but some questions have been presented enough. I just don't want to see them anymore.
Okay, it's
No,
understandable.
this is a question based on like a 7A and 9.
Yeah, so
Yeah,
it's
I know.
9. Though.
It's 7, 1, 2, 3, up to 7. So I heard you says, and then
How
not
far
from
ahead
7
can
to
I?
7. So now I base on like a 8 and 9.
Yeah, because this one, according to my knowledge, I have seen enough.
How far ahead can I like take
I think
questions
the first
from?
time, right? I guess. The last time nobody present that like a 8 and 9.
Hold on a second.
Yeah, up to 7, because I read the recording from the last on Tuesday. I remember only one person, but he make like own one. So.
Okay, David, you already reached 60% of your presentation, and Su Xian.
I only 4.
Su Xian also 60. There's no point. No. I don't want to see these kind of questions anymore.
Sure,
That's
sure.
enough.
But can I
Okay.
do a question from like 2
No,
chapters
you need-
ahead? because
Okay,
people have taken all the questions already from the next chapter.
Hold on 1 second. First, you do not have to present every class. That's no point of it, okay? You don't have to present every class. I really want those students who hasn't presented, or who has presented only once or twice, catch up with the rest of us. And some of us already reached the 5 presentations, 6 representations. That's good enough. You don't have to present every class, all right? And let's see.
But I just enjoy it so much, you know.
Me too, David. Me too.
All right.
Agree.
Okay, sorry guys. Let's see. Hold on 1 second. And I'm a little bit behind my schedule. Yes, Gregory.
I had a question. Oh wait.
Yeah.
If there aren't enough questions, right, for everyone to present,
Right.
then we would present a little bit or a topic ahead.
Yes, some people are already doing it, like Ryan and Anchi.
Sure, I'll try, but you know, it's
I'll
kind
be
of hard to read the notes, you know, without like
I
someone
understand.
explaining it.
I understand it. Yeah.
Yeah.
So okay, let's hold on 1 second. Let's finish this. Let's do. Anybody else from 7? So far, Ryan, yes.
I wanted to present a question that I saw something similar in 8, but I actually wanted to present it in the context of 7. It's a third order differential equation.
Third order. Let's leave that. Let's leave that third order. Let's go with the second order. Okay. Anyone still have? Okay. So if you have presented a question once, you don't want to present it twice, similar questions, all right? And you don't have to present every class again. And so far, I think we, let me see. So now, okay, Anchi, let's go with yours, 8.2. So because this is new to most of us, make sure you explain what's going on. Okay, you explain what you have studied yourself and what do you apply in your question. Okay, go ahead, Anchi. Oh, Ronald wants to present the one. Ronald, I have major presenters.
Hi, sorry. Hi, can you hear me?
Yeah.
Yes, okay. Let me just pull it up quickly. I'm gonna have to exit and I'll come back in 2 seconds. I have to switch computers.
Ronald, are you ready?
Yes, I'm ready.
Okay, maybe you can go first.
Mhm.
Hi, can you hear me okay?
Anchi, you good?
Yes, sorry about that. Here, let me share my screen. Share application screen. Entire screen. All right. Good?
very blurry.
Blurry?
Now it's okay. Now it's okay.
Good? Okay.
Yeah.
So I'm presenting 8.2. It's similar to what we did before, except in this case, instead of a 2 by 2, we have a 3 by 3 matrix. So that means instead of 2 functions, we have 3 functions that we're looking at. So I'll pull up question homework 8.
She's talking about Wronski. Okay. Still using
Yes.
Wronski.
But this one,
So you are checking, are you checking the 3 functions are linearly independent? What are you
Yes.
checking?
Yes, correct. So I have this homework pulled up. So 8.2 asks, use Wronski to show that the function in problem number 1 are linear dependent. And I have their functions written here. So f of x is x, g of x is x squared minus 2x, h of x is 8x minus 2x squared. And again, putting into the Wronskian format, which is very similar to the 2 by 2. Except instead of taking one derivative, you have to take a derivative again, which is right here. So f of 1 to the derivative of n minus 1. So here the derivative of x is 1, take out derivative again 0, you do the same thing for g of x as well as h of x. Sorry, one moment. You can drop me off just by bus station, please. So now we can take the determinant of this 3 by 3 matrix. And thank you. Sorry. Okay. And the equation for the determinant of a 3 by 3 matrix, I have the equation right here. You take A and you times the determinant of EF HI. So the easiest way to look at it is if you're taking A, you block the whole column out, and then you take the determinant of this 2 by 2 matrix, and then minus B times df, the determinant of dfgi. So again, you block B column, which is number 2 column, and you take the determinant between dfgi, and then you plus C times the determinant similar as before. You block the C column out, and then take degh. And the key here is you have to minus and then plus. How I remember it is it's negative, positive, and it keeps going on as your matrix size increases. So over here, I just follow exactly as the formula up top. So A is x, and then I put the determinant of the 2 by 2 remaining matrix minus B, which is x squared minus 2x. Again, the determinant plus ax minus 2x squared. Again, the determinant. And then as I presented from last presentation, the determinant is just the cross-section product of these cross-section minus the product of these cross-section. So that is 2x minus 2 times negative 4 minus 2 times.
No, you don't have to read the calculation. You can skip that.
Okay. Yeah. So I did the same thing for this whole formula, and then essentially you just have to FOIL it out, and then you find that the Wronski is indeed equal to 0, which means that it is linearly dependent, because as we recall, for it to be linear dependent, the Wronski has to equal to 0. And that's
Great.
it.
Okay, great. Anyone has any question?
No questions, but get home safe, friend.
Okay,
Yeah, very
thank you.
clear.
No
All right.
problem. You're great.
Yeah. Okay, Ronald, back to you if you want.
No problem, está.
Okay, I think he has some internet connection problem. Okay, Suzanne, 8.3.
Okay.
Thank you.
Jumping jacks won't matter if you keep them. If the cable is about to break, you're dead either way.
Oh, really?
Yeah. Oh, sorry.
Is it?
What?
One second, Professor.
Okay. Oh, hold on. Hold on. Actually, oh, okay. Christian's question is based on 8.3. All right. So after Susan, maybe Christian, get yourself ready.
Okay.
Can you see it?
Yeah.
Okay. So my question is somewhat similar to the last one. We're trying to find if the Wronskian if it's linearly independent on R. So the equation was e to the 2x, e to the 4x, and e to the 6x. So I put it into the Wong screen right here. So I have e to 2x, and then 2, 4, and the same thing for the other two. And then when I compute it, it's going to be the first one minus the second one and then plus. So it's minus plus and then minus plus. So put that into the equation. I ended up with 12e to the x minus 6e to the 12x. And when I solve the 3, it came to 18e to the 12x was the final answer, and that is not equals to 0. And we know if one screen is equals to 0, then it's linearly dependent, and if it's not equals to 0, then it's linearly independent. So
Okay.
that was the answer for that.
Okay. All right. Anyone has any question? Yeah, mathematics is just like that. David, you can, of course, try to self-study because mathematics is just like building a house. If you have the proper foundation, just keep going, keep going. You see the Wronskian, you can go to the higher level, you can check finite many functions if they're linearly independent, right? You just keep doing the derivatives. All right, that's Christian.
Yep. This is my version of question 3. The question that the original question for question 3 involves 3 base e functions. However, I chose 1 base e function, and the question is as follows: use the Wronskian to show that f of x of e to 25x and g of x, x squared plus 5, and h of x, which is equal to x, are linearly independent. So what we're trying to find is the Wronskian and seeing if the Wronskian is not equal to 0. Because if it's not equal to 0, like everyone just said, it is independent. If it's equal to 0, it's dependent. When you're putting it into the Wronskian, you're going to have a matrix that is square. It's going to be a 3 by 3 matrix. Previously it was 2 by 2, but now it's 3 by 3. And the first row right here is just going to be the functions that you're presented with, which is e to the 2 power of 25x, x squared plus 5, and x. And then as you go downwards, you're going to derive. So you take the derivative of e to the 25x, you get 25 e to 25x. Do it again, you're just multiplying by 25 again, so you could just say 25 squared multiplied by e to 25x. Same thing right here. derive this, you get 2x and then 2, derive this, 1, and then 0. And what I did differently compared to my other peers is that I computed the determinant in a different method, which is called the diagonal method. What you can do is just add the additional first two columns of your matrix to the same matrix that you're presented with, and then you could do a cross multiplication in a way. So from this corner on, you go down, multiply here, multiply here, multiply here. Same thing for the left side of your matrix, and then you have these two different components that are going to be subtracted from one another. The right side is going to be subtracted by the left side, which I showed the arrow being pointed right here. The right side of this matrix over here being placed over here, the result of multiplying across, and this 2 over here to the right. So it's sort of like a weird switch up. It works for me. So yeah, I did my computation. I distributed my negative right here. I'm not going to like tell you the whole thing because it's very large. It's a large expression. And then as I did my computation, I expanded it out. I found two like terms. I brought them together right here, negative 2e. And then you have this other e function, and brought them together, got my Roskian. It's not equal to 0. Therefore, your functions are linearly independent.
Great, great. Yeah, the new method, the method, yeah, that's another way of calculating. If you have some linear algebra background, yeah, there are many ways to deal with the matrices. All right, anyone has any question? All right, I think next one, who's next one?
I'm ready, Professor. I'm sorry. That's Bernoulli.
Oh, Ronald, okay, go ahead, Ronald.
Okay,
Oh, okay, Albert's next one. Then 5. Excuse me. Or GE5. I think then
wait. Sorry. It's not working.
you know how to share your screen?
Yeah, I'm trying.
Okay. New era of education. Right. I still remember first semester when COVID hit. Oh my goodness. I cannot find my students couldn't find me. That was really chaotic. But after COVID, you know, things just changed. I think the GE, David, the GE is going to do question 5. Ronald, what are you trying to do?
I'm trying to get my email so I can open the link that I sent to my when I scan my homework. So I'm just trying.
Can you get yourself ready? So let GE go first. Or maybe Albert, let Albert go first. You get yourself ready, Ronald. Okay, Albert, you can go.
Okay, thank you. I'll share my screen now. Let me see. Here we go. Let's see, should be going up now.
Yes.
See it?
Yeah, it's clear.
Okay, so it was a little difficult actually. Oh, it was a little difficult actually because I had to try to learn ahead. I watched some YouTube videos, so I don't really know if it's correct, but this is what was given to us, that y to the third derivative minus y to the second derivative minus 5 to the first y to the first derivative of 6y equals 0. And it's a linearly independent solutions where y1 equals e to the x, y2 equals e to the minus 2x, and y3 equals e to the 3x. And the question asks for the particular solution with these three different points. So the way I saw online how to do it was the method of variation of parameters. That's what I wrote there. The way that that I had it was a ypx, which I looked later in the notes here. I have the notes printed. It was also px. Where is it? It was, we had to try to get the general solution, then had to get it down to the particular solution. Sorry. Anyway, so there's this equation there that we had to plug
Excuse me,
into.
Albert. You need to get yourself
Yes.
ready. When you present something, you cannot doubt yourself. You need to show us.
I need to show the confidence, right?
Yes, you gotta show with
Okay.
confidence. You
So
did
I have
this.
y p of x equals
did.
u1 x e to the x plus u2. So we basically have three coefficients. We have one coefficient for each of our three y's here. Our y1, y2, and y3, which is our three linearly independent solutions, each with a coefficient, and that is going to be our general and then particular solution once we use the three different points.
So let me ask you this. This is a very important part.
Yes.
Can you see my screen?
Yeah.
This is a very important part. This comes from in the first half of 7. See, if y1 is, that's only for two functions, but it's good for finite many. If y1, y2, in your case, y1, y2, y3 are solutions to a third order equation, C1 plus you use U1, U1, y1 plus U2, y2 plus U3, y3 will be a general solution for that, for the third order equation. All right, this works for finite many. So this is a very important point. Okay, keep going.
Right. Okay. So yeah, so that's what that was. So to get this, I got the first, second, and third derivatives over there. They're very long. Do we have to go through the computations? I don't think we do, right? This is the first, second, and third derivative of that yp of x. That is u1 e to u1 y1 u2
You
e
don't need to read it.
y2.
Let's skip that.
Okay.
Let's skip
So when we plug it back in and simplify, so for the e of x, we got y to the third, u to the third derivative. So those all equals 0. So that's what those next three lines there are plugging back in. And then when we look at the perspective of the 3 points that we had, the y of 0, the y prime of 0, and the y double prime of 0, equaling 0, minus 4, and 14. And then now, if we make x equals 0, right, in e of x, e to the minus 2x, and e to the 3x, if we make each of the x's 0, so then that's what I got it simplified down to. And then once I solve the system of linear equations on the bottom, on the side, so u1, u2, u3, u1 prime, and u2 prime all came out to 0, and u3 prime came to minus 2. And so then I got my solution, which to me, I mean, without learning the material, seems to be minus 2 e to the 3x. That's what I got as my particular solution here.
You wrote it as y1 of x equals negative 2e to the 3x.
Yes, that's what I wrote on the bottom there.
y1.
Not y1. No, sorry, yp. That was the equation that I had on the top, the one that you circled.
The one you circled, yp. Oh, yp.
Yeah.
Yp. Oh, that's p? Oh, the p of
It's
x?
supposed to be.
Yp
I don't
of
know.
x.
Where I learned it online, where I searched it online, it had yp of x. That's what it called that equation. I'm not
So
sure
you
what
have
the p is for.
right, because your goal should be solving for u1, u2, and u3. But I
And
see you
u1, u2, and u3. So u1 and u2 and u3 are all 0.
u1,
But I got
u2.
for u3 prime, I got -2.
If u3 prime is negative 2, what's u3? Because you need to find u3. You need to find u1, u2, u3. Right? You cannot use u3 prime to substitute into this. And also you cannot use u1 prime, u2 prime value to substitute into the yp of x.
Right. Oh, so if I got u3 prime to be -2, that means my x, that means my u3, if y3 equals e to the 3x, that means I should be getting, so -2/3, or
You know what? Okay, I'm not going to give you credits for this. Fix this, show again next class. All right, I'll give you full credits. Fix this. You haven't finished yet. But it's good. It's a good try. It's a good try. Maybe after today's class, after 8,
right,
I don't know if I'm able to talk about finish 8.
right.
Maybe after today's
I
class,
wanted to do a question from an earlier problem set, because that's what homework, the homework is from previous ones, but I think they were all taken. So to get
exactly.
my presentation credits, I tried to, go into the next thing.
I understand. So far, we have students already presented 5, 6 times. And for those students, remember that you don't have to present every time, all right? You don't have to
Right, but
present
this is
every.
only my second time presenting.
I know, I understand you, I understand it. That's why, because I won't give you full credits for this, but I'm thinking you can fix it. You can fix it, so next time, you just quickly show us, I can give you full credits. Would you like that?
Okay.
Okay, thank you.
Thank you.
Okay. All right, I think Junyi, you're the last one.
Okay. Give me 1 second, please. 8.5.
Oh, actually did it wrong. Oh,
You want him to go? I'm okay to that.
Okay, since yours is up already, let's finish yours, then we go back to that. Yeah.
So basically, this is to find the solution. 1 second, let me see that. Okay, so it's find the solution to the given initial value problem. So from the note, what I got for is here, like, sorry, it should be a capital Y, not the lowercase. So it's the general solution equation would be capital Y equal to y sub c plus y sub p. So y sub c is the complementary function, which is a solution of the homogeneous equation. And the y sub p is the single particular solution to the non-homogeneous equation. When adding them up, is equal to any solution of the non-homogeneous equation, which is the capital Y. So that's the equation I have to use to solve these problems.
All right, so you're using a lot of new terms to us. because you're using it, because you went ahead of us. Would you please, anything is new, would you please give a little bit explanation?
Yeah, sure. Like, for example, like the non-homogeneous solution, which is like the equation given here for the number 5, which is the y double prime plus 9y equal to 18x, which is not equal to 0 for this equation. It's equal to somewhere like some certain constants or with the variables like 18x. And it already given the y sub c, which is what c1 cosine 3x plus c2 sine 3x, and the y sub p equal to 2x. So all I have to do.
What does yc mean? What does yp mean? What does yc, yp mean?
That's yc is the homogeneous, the solution of homogeneous equation, and the yp is the solution of a single particular solution to the non-homogeneous.
Okay, thank you. Keep going.
Okay. So, and also given by the initial value, y sub 0 equal to 3, and y prime of 0, which is the first derivative of y, equal to 7. So what I do is just adding them up, like y sub c plus y sub p, which is equal to c1 cosine 3x plus c2 sine 3x plus 2x. So the next step, I take their first derivative of y, which is the y prime, is equal to negative 3c1 sine 3x plus 3c2 cosine 3x plus 2. Then, so I can plug in the initial value, like the 0, y sub 0, which is equal to the whole equation, equal to the 3. Then I can get c1 times 1 plus 0 equal to 3. So the c1 is equal to 3. And then plug into the first derivative equation, which is equal to 7. The y primes of 0 is equal to negative 3c1 sine of 0 plus 3c2 cosine of 0 plus 2 equals to 7. Then finally, I got the 3c2 equal to 5. Then the c2 is equal to 5 over 3. Then I plug in back c1 and c2 to the general solution to the y double prime plus 9y equal to 18x. And it's finally I got y equal to 3 cosine 3x plus the 5 over 3 sine 3x plus 2x.
Great. Anyone has any question? All right. So
okay, thank you.
Ronald, are you ready? So that's G.
Yeah, I'll try again.
Okay. So my plan today is to finish 7 and 8. Let's see if I can achieve that.
Number 1 from 8.
What's your link? What's your link?
What's a link?
Yeah.
Oh, wow.
We don't see your work yet. You need to bring up the screen which have your work. This shows you Gmail. Gmail with a link.
I don't know why it's not loading. All right.
You can always present next time when you're ready.
No problem.
Would you like to present next class? Yeah, I think he has a internet connection problem. Okay. Let me share my screen. Oh, Ryan, yes, I forgot about you, Ryan. Yes, go ahead.
I'll be quick, promise.
Okay.
So I wanted to present sort of, I know it looks similar to the other ones, but as you can see, it's a third order. And I saw a lot of third order questions in the next homework, and they all had basically check if the answer is correct, right? Like a couple of presenters already showed. I wanted to actually derive the answers. So in this case, it's a very specific third order linear equation. There's a plot here of I took the y primes and I converted them to x to the power of however many primes there are to get basically just a cubic equation. And as you can see, there are roots. All three roots are real numbers. And that's important because that won't give us any sines or cosines. So we can just use, again, e to the rx. But when we plug in, we basically end up with this. So we can factor out one term of r. In this case, the way to do it is just use the last term, plug in the factors of the last coefficient, and when the whole function equals 0, that's a root. So in this case, one of the roots is r equals 1 or r minus 1, and then dividing will give you the other factor. And so, of course, we know how to do this. So we have r equals 1, and then just quadratic formula for the rest. And here's our other two roots. I just found a general solution because we know how to plug in numbers at this point. And so the general solution in this case has 3 terms of e to the rx. On top of that, if you notice the plus 2, that's from over here. I didn't set it to 0, I set it to 2. And so what ends up happening is I just have to shift the function up by 2 because everything is 0 when x is 0, in this case for this differential equation. So that's basically it. I also have a plot that I can show that shows that the solution works. Do you want to see that?
Yes, quickly.
Okay.
Yes, David, get yourself ready.
I'm going to share the screen for a second. It's going to be a bit wonky, but it's right here. So this is our whole solution where C1, C2, and C3 are constant. And if you basically take the third derivative minus 3 times the second derivative plus the first derivative plus the function, you can see it equals 2 everywhere. So therefore, our answer is correct.
Nice. Okay. Thank you. Okay, David.
Okay, so I just did this problem right now because I just love presenting so much. Here it is. I think this is right. I need to find a particular solution to, I'm given a complementary solution, y of c in a particular solution, and y is basically the sum of them both. So I did that, y of p plus y of c, and I get this equation right here in the fourth line down. And then I kind of skipped a step. I just started taking the derivative. I took the first derivative of that. There's some product rule in there, derivative the first times the second times derivative second times the first. Then you just tack on x plus 1 at the end. And then I plug in y of 0 equals 5, y of prime of 0 equals -1. There's some math, basically anything that goes into the zeros that go into the signs make the sign 0 and then cancel out the term. E to the 0 is 1, so that's where all the 1s are coming from. first derivative of x is just 1. So after some algebra, we get this equation, negative 2c1 plus 3c2 equals 0. And then we can just plug in 0 for the original y equation, which is the combination of y of c plus y of p again. And then we get this equation right here where it's basically just c1 plus 1 equals 5, so c1 equals 4. We could solve the system of equation by plugging in c1 over here. I just realized I made a mistake. I put a 5 instead of a 4 inside there. So the actual solution should be 8 over 3. And so here's our final solution, y equals 4 of e to the negative 2x cosine 3x, and then plus 8 over 3, not 10 over 3, e to the negative 2x sine 3x plus x plus 1.
Okay, all right, thank you. All right, finally, it's my turn. Let's finish 7, going to 8 today. Oh, we talk about this. We talk about Wronskian. Yeah, this is the way I remember Wronskian, right? It's all about the F and G. Yeah, this one is saying if M and G are dependent, you have this because you get 0. Right, we did talk about this one, right? And I was also talk about this theorem too. Okay, let's read this. So linear second order equation with constant coefficients. We didn't talk about this, right? So a y prime, did we? We did. This is divided by a on both sides. Oh, let's see. Let's just quickly go through this. Right, we have a coefficient before y double prime. We have a coefficient before y prime and before y, and this also equals to 0. The y is defined as e to the rx. And this is a special one, right? Because the y defined as e to the rx. And then y prime just r times y. And then y double prime just r squared times y. So that's why we can factor out y. We have this quadratic to work with. And many of you have showed your homework already. So we just solve the quadratic equation, right? Get 2 solutions. Then in this case, so we have a general solution to be like this, right? This is our y1, this is our y2, we have a c1, y1 plus c2, y2. Let's see this one. Find a general solution to this. I think by now we should be very good with this. And y is still the same y, e to the rx, y prime is ry, y double prime is r squared y. Again, we're working with a quadratic. You know, if it can be factored, we factor out, so we get our general solution. If anyone has any question, feel free to stop me at any time. Find a particular solution for this, right? Given 2 points, 1 point for function y, 1 point for y prime. Because we have 2 unknowns, so we need 2 equations to find those 2 unknowns. You know, very similar. We just plug in the value, right? Solve system of equations. So we have this system of equations, solve for C1 and C2. Then we'll get a particular solution, all right? Because it's a second order, so we need 2 initial conditions, 1 initial condition for y, 1 initial condition for y prime to solve for second order. And as you keep going, right, if we solve for third order, so we need 3 initial conditions. Fourth order, 4 initial conditions, so on and so forth. So find a general solution for this. Right. Again, the y is the same y. Okay, y prime is r y, y double prime is r squared y. So, you know, all we left is to work with this quadratic. Okay, let's see this one. This one saying what happens if we get a double root in the equation, which means we get a perfect square. When we try to factor out, we see this is a perfect square. Okay, we have a perfect square. So which means the two solutions are the same. We call double root because the multiplicity is 2. Multiplicity with the root 2 is 2. So in case that, so then y equals the x times e to the rx is also a solution, right? In case of a double root. So we check this, y prime is this, y double prime, we do the calculation, and then we substitute y prime, y double prime. We see that also satisfy the equation equals to 0. So what is the general solution? The general solution is C1y plus C2y times x. Okay, so e to the rx. Okay, any questions? Su Xian, question?
Oh, yes. Okay. Why you said like in case the rule is y equal x, that is times e
All
over
those
x.
examples, right? All those examples we're working with, y equals y is defined as e to the rx.
Right.
Yeah. So what else? What's your question?
No. Y equal like a e r x, right? It's not x times e r x like this.
No, this is in case we have a double root. In case the quadratic we can factor out as a perfect square, the two roots will be the same. We call double root. Double means the multiplicity of 2 is 2. So in that case, so y equals to xy. So not y equals to xy. Okay, just another way. Think about this as a y2. Okay. Think about this as, okay, this y is not so good. Think about just another solution. X times e to the rx is also a solution.
I don't know where you can get like that solution y equal this one. So
this is just telling you. This is just telling, telling you if that's a perfect square. If the quadratic happens to be a perfect square, it seems like you only have one solution. No, in that case, you have another solution. It's x times e to the rx.
Okay.
The x times y. Let me see if anyone has comments. And oh, okay. Not to worry. So this is checking. This is to show you why it's also a solution. This is a given. This is a fact. In case this happens, this is a fact. This is a checking to see it satisfies the equation. So in that case, the solution is this. Ryan?
Sorry if I cut you off. I was just curious. So if we have a triple root, would it be x squared times e to the rx?
Yeah, go ahead to check for yourself.
Okay.
Good question. I don't want to answer you. Very good question. Go ahead to check for yourself. Great question. Okay, so notice here y1 is this e to the, or notice y1 equals e to the 2x. y2 is x e to the 2x are linearly independent because this shows you the Wronskian is not 0. All right. So this just use one example. So this is that's a general solution for when it happens to be a perfect square. All right, that's 7. Anyone has any question? I think we're pretty good with 7. Because many of us have showed, have presented. Okay, let's go with 8. higher order linear differential equations. Many of you already presented the questions, and I just have to clear some terms. Now, nth order, okay. So first order, second order, third order, up to nth order, finite many. Finite many. Order linear differential equation is of this form. All those symbols are just, all those symbols, just a symbol of a function, okay? You see, this is a function in terms of x. Y to the nth derivative. This is another function of x, y to the n minus 1 level derivative, so on and so forth. Another function of x times y prime, another function of x times y equals to some function of x. So in this form, those p0, p1, not important, right? Just a simple. What's important is the function of x. Function of x, function of x, function of x, function of x, function of x. If the coefficient of the nth level derivative is not zero, if this one is not zero, right, that's this one, then we can divide the above equation by this one. Then what do we get? We get this in this case. We get a y to the nth level derivative, right? The coefficient becomes 1 now. Then this is a P1 divided by P0, so on and so forth, so on and so forth. And this little f is a capital letter F divided by P0. And we call this, and of course, right, we have something like this. If this one is 0, and we call it associated homogeneous equation, right? Remember, it comes from before. It's just extended to nth power derivative, nth level derivatives. Okay, theorem. So let y1, y2, y3 up to yn be n solutions of the homogeneous linear equation on the interval I. All this is to be mathematically correct, because whenever you take derivatives, whenever you work with derivatives, right, the domain has to be an open interval, because otherwise you wouldn't be able to take derivatives on the end, on the boundary. C1 up to Cn are some real numbers. Then the linear combination, C1 y1 plus C2 y2 plus da 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 up to Cn y1 up to Cn yn is also a solution to the homogeneous linear equation on the interval, right? And usually, so it's the same as, the proof is the same as n equals to 2. So let's see some examples. So y1 is e to the negative 3x, y2 is cosine 2x, y3 is sine 2x. Are all solutions to this third level derivative, differential equation, right? And we want to show this one is a solution as well. Well, let's see what's the difference. So this is a y1, and this is a y2, and this is a y3. This is a C1, C2, C3, right? We'll just have to take the derivatives. Sometimes we use y3 apostrophe to indicate the third level of derivative of y, or just a y with this symbol, y raised by 3 but with open parentheses and close parentheses to indicate this is the third level of derivative of y. Okay, why is this first level derivative? right? Second y prime, double prime, second level derivative, y triple prime, or you can write as y. So those two notations are the same. Okay. Y triple prime, or y to the third level of derivatives. Then we just add this triple prime with 3y double prime and 4y prime, 12y, and indeed they equal to 0. So similar to before, if y1, y2, y3 are linearly independent solutions, then the combination with some real numbers are a general solution, same as before. Before we only have C1, Y1 plus C2, Y2. This extends to N, all right? If Y1, Y2, Y3, da 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 da, up to Yn are linearly independent, then the solution is C1, Y1 plus C2, Y2, da 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 da, plus Cn, Yn is a general solution to the nth level derivative differential equations. Theorem again. Suppose P1 up to Pn and f, little f, are continuous on the open interval I, to be mathematically correct, containing the point A. Then given n numbers, B0, B1 up to Bn minus 1, the nth order linear differential equation such y to the nth level derivative, n minus 1's level, y prime, y, this is P1, a function of x, da da da, function of x, equals to some function of x, has a unique solution, all right? So has a unique solution. This is also similar to before, right? Before when we talk about first level, second level, maybe second level, right? We talk about the same thing. Yes, the second level, when we talk about the second level. So what if, so y of A equals B naught, y prime of A equals B1, right? The n minus 1's level of A equals B n minus 1. Before we talk about only y of A and then y prime of A, right? Let's see an example to make this idea concrete. So let's see why have this is a general solution to this equation, to this third level differential equation. So we want to find a unique solution given these three initial conditions. You see, third level, we need three initial conditions. We start with y, right? Taking the first derivative, y prime, we get this. Second level derivative, we get this. Plug in initial value. Plug in initial value for y prime. Plug in initial value for y double prime. Because we have C1, C2, C3, we have three variables, right? And we need three equations to solve. Three variables, three equations to solve for each variable. So we have a system of three equations we can solve, right? Doesn't matter which way you solve. You get C1 equals 1, C2 equals 3, C3 equals -1. Now we get a unique solution. Before we call particular solution. Get a particular solution for such three initial conditions, which is such. Anyone has any question? Okay, let's keep moving. Similar as before, similar as 2. Now, n functions, f1, f2, up to fn, are said to be linearly dependent on the interval I, provided that constant C1 up to Cn, not all 0, some of them can be 0, such that linear combination equals to 0. The linear combination equals 0, and it is said to be linearly dependent. Okay, linear dependent. If the linear combination equals 0. Let's see an example. We have a constant function, we have a cubic function, we have another cubic function, and we want to show the linearly dependent on real numbers, on all real numbers, right? Domain is all real numbers, domain is all real numbers, domain is all real numbers. So we talk about all real numbers. So we need to show we can find such 3 numbers, not all 0 at the same time. And then if we put in, we get this one equals 0. So which means C1 F plus C2 G plus C3 H equals to 0. Okay. So plug in F, G, and H, combine like terms, simplify, we get this. So let's see this. We get these 3 constant terms to be 0 because the other side is 0, right? And also we get this to be 0, right? So we get 2 equations. We get C3 minus C2 equals 0. 4C2 equals 0. We get this equals 0. How many variables we have? We have 3 variables. Those are the only 2 equations, not enough to solve for C1, C2, C3. So that's why what do? We said, okay, let's just let C2 be, well, could be C1, could be C3, right? Just let one, just pick a value. Just pick a value. Just pick a value for one of these C's. Let's pick a C2 equals 1. If C2 equals 1, because we want to pick C2 or C3, right? If we pick C1, it won't work. We still have, oh, we could solve for the system of 2 equations, right? So in this case, we just pick C2 equals 1. We solve for C3 equals 4. Then we solve for C1. C1 equals 2 over 3. We'll just plug in. If we plug in, indeed, we get 0, right? Get 0. So this just to show, right? So by the definition, and these 3 are linearly dependent. And of course, you can see that, right? You can see that. You can see the linear combination. You multiply something with F, multiply something with G, multiply something with H. You could make the linear combination to be 0. Because this is just constant. This is just constant. This is just constant. And these 2 terms are like terms, x cubed term. Yeah, in other words, you can write one of the functions in terms of the other 2.
Is it just me or for everyone?
I guess we're taking over.
Yeah, okay. So,
Does anyone want to present from anything from section 8?
yeah, sure. So, if you can
Shit,
get...
my mic wasn't on, guys. Oh, I'm so sorry. I was volunteering.
Okay.
Yeah, are we on a section 7 or 8?
8.
8.
Okay, guys, no problem. I got you. Let me just pull it up now.
Can you explain can you explain on page 1 the first example?
Oh,
why
okay.
does that? Yeah.
This one?
Why does go down the first example? Like, why does that why does that show that that's also a solution? Like, you just take 3 derivatives and now all of a sudden it's a solution. I didn't really get that.
Okay.
Yeah, that thing.
Let me just try to remember from my notes. So remember from section 7. Let me open that one up. I think. Oh God.
He has it right.
That's 7. So I need 8. Okay, guys.
Hey! Whoa! I just was referring back. I'm so sorry.
I need help. Okay.
Okay. No problem. Shu, do you know how to explain this one?
You asked me?
Yes. This example, can you explain this one to us again?
No idea.
Oh. Well.
So I need the professor explain. So professionals explain that. So very clear.
Right.
So
right.
I am not. I'm only students. I only present.
Me too.
I get ready.
Okay.
Yeah. Okay. I'm so poor. I'm so sorry.
No, you're perfectly fine.
Does it just...
Rio, thank you so much. Okay. Yeah. Oh, that's 8. Okay, go ahead.
Yeah. So I think from what we were doing with 7, we just had linear differential equations, and then we had like secondary something, whatchamacallit? Yeah, second order linear differential equations, right? So we're just gonna go ahead and continue that idea. All right, David, here you go. Take it away.
I'm the one who asked for help.
This is the most explanation I got so far.
Okay.
Yeah.
So the first example, it's like you just take 3 derivatives of the third order homogeneous equation, and it somehow proves that the given formula is also a solution as well.
This one?
Yeah, I'm not quite sure why that one is a solution.
Let's ask Kate. I think she knows. No, Liz. Liz is pretty smart at this class, actually. Can you help us?
Yeah, can you help us?
Yeah, of course it's recording, but we're trying to understand what's going on.
Yeah.
So. You can't.
What?
Come on.
We were counting on you. You are our actually no. Our last hope is Ryan. Ryan.
Is Ryan here?
Yes, yeah, I think I know. It's because when you derive it and then you integrate it, you get back to the same thing. So obviously, that's the answer.
Oh no, that actually makes a lot of sense. But
wait, but how?
Thank you, Ryan.
Okay,
wait, why?
I'm sorry, David. Please continue.
Yeah, how does that show that that's a specific solution as well? Because, what is this? Oh wait, hold up. Yeah. Never mind. You're good, thanks.
Wait, David, do you understand this page?
Yeah, I'd say so.
Can you just start explaining to me from the top again? I'm kind of...
Alright, yeah, sure. So, okay. It's basically just an infinite series, right? Where you just start with p of x, I believe is just something in front of
coefficient.
You could think of it as that. I mean, it could be a function as well. And when you take the first derivative, you're just going to end up with more stuff in front, right? And that's what I assume is going to be p1, and then you take the derivative, so you subtract 1, and then you just keep on doing this until you reach p of n, which might be wherever it is, right? So it's like a series. And then if p of x equals 0, does not equal 0, then you could divide it, and I suppose that's just what the small p's are. I'm not sure.
You know what? I get it. Okay. Listen. So back to this one is 7, right?
Yeah.
So remember how like this is slide 1. So these terms, like the coefficients, if you divide it by whatever you divide it by a of x, which is the term on you know, the y double prime,
Right.
the remaining coefficients, they become like the small p of x, and the big one becomes this is actually a big f of x divided by a of x.
Yeah, it's kind of like,
yeah.
I think they're trying to like separate. It's kind of like separation of variables almost, because then you can get that y of n by itself in the beginning.
Yeah.
So I'm not quite sure why, but yeah, I'm sure we'll figure it out.
That kind of makes sense. That kind of makes sense if it's the third order, you know, take the third derivative,
right,
so on. Yeah. Okay. That makes a lot of sense.
Yeah.
Okay.
Yeah. Okay.
So I guess I'll just brush past. I don't know, dude. I really don't know.
No, we know. We're very highly intelligent. Okay. You gotta have more faith in yourself.
Of course. I will be a little more confident.
Yeah.
Okay. What about this?
Okay, suppose P1 to P to the n and f are continuous on the open interval I containing the point A, then the given n numbers b0, b1, all the way to bn minus 1, the nth order linear differential equation, that line has a unique solution on I with y of a equals b0, y prime of a p1, and then so on and so forth.
That makes sense.
Yeah, no, it really does.
Okay.
And so, I'm guessing, we kind of went over this, but I guess you can do it again. So the example is asking us to find a unique solution given the general solution. And so what you can do here is simply because we have 3 solutions, so we just need 3 equations, because, you know, you need 3 equations to find 3 different unknowns. And so we just derive twice and then plug in 0 and set it equal to the number. And so that's just going to give you the values, and then you get a system of equations, and then you could just solve the system of equations. And that will give you, your constants, which you could just throw back in.
Nice.
So that's, that one's pretty clear.
That was pretty simple.
Yeah, and so for this part, the idea is that they're linearly dependent if you can get them to sum up to 0 with certain coefficients. So kind of like in
what, the functions are? The functions have to be summed up.
Yeah, like the sum of all your functions with coefficients of f of x, g of x, and h of x. Remember how in linear algebra, if you can solve the system of equations in a matrix or whatever, it means they're linearly dependent, because basically that means you can sum them up and get them. They have
coefficients, right?
Yeah. So in this case, we're doing something kind of similar. We're just getting towards a system of equation. Rather, we're making a system of equation, adjusting it so that it can equal 0. And if we're able to do that, that means they're linearly dependent. And so basically what happens here is you set up the constants in front of their whatever the functions, and then you distribute, and then you could pull out whatever's associated with x. And then if you remember from like basic algebra, if you just have a bunch of constants that relate to a certain variable, you can set those equal to whatever's on the right side of the equation. And so that's what happens here with the C3 minus 4C2, and then the 3C1 minus C3 plus 2C2. And then you could just make another system of equations, but there's one missing variable. So basically, we're going to have to make one of these 2 equations equal 0. We can do that easily by making C2 equal 1 and C3 equal 4, and that satisfies the equation on the left. And then we can basically just find the other one, C1, by just plugging those values into the second equation. And because this works, we know that they're linearly dependent on out of the set of real numbers, I guess. Okay, the next section. N functions f1, f2, all the way to fn are linearly independent on interval I if the sum of them with constants in front equals 0 only when C1 equals C2, which equals C of n, which equals 0. So basically, the null solution is the only way that they're linearly independent.
Trivial solution. Okay.
Yeah, trivial.
Gotcha.
You're right. Okay.
Okay.
And so the example given is show that f of x equals x, g of x equals x squared, h of x equals x plus x cubed are linearly independent on R. And so I need more highlighting. That's
sorry.
Integral part.
Yeah.
Start highlighting stuff. Thank you. We need to show that any C1, C2,
so
and
sorry.
C3 of C1, C. Doing great. Okay, C1F, C2G, and C3H equals 0. I assume that F, G, and H are all just functions, and then, as you know, the C's are constants. And so we need them to all equal 0. And so this problem's kind of funny. Yeah. So you just make them 0. There we go. Yep. That's how you do this problem. Okay, and so I suppose we're going back to the Wronskian.
Yeah.
It's a miserable name. I don't really like it.
I don't know why they didn't just call it
Agreed.
like, a matrix of whatever size. But yeah, you're doing great.
All right, thank you. Okay, suppose f all the way to f of n are n minus 1 times differentiable on an open interval, which makes sense,
Can you
right?
explain why not n? Yeah, go ahead.
Yeah, so let's say you have x to the third. You are going to be able to differentiate this twice, right? Until you get, let's see, x to the third, 3x squared, and then 6x, and that will give you something with x in front of it. And I suppose we're just trying to avoid getting a constant, right? Because if we do x to the third, let's say 3 times instead of 2 times, that would give us just 6, right? And I suppose we don't want that because then it won't be a function, it'll just be a constant. And so that's why, yeah, n minus 1. And so it's the Wronskian is linearly dependent functions of n linear dependent functions is 0. So to prove a set of n functions is linearly independent, we just need to show that the Wronskian is non-zero. And we kind of remember this from the other chapter, right? You just need to get something that's not 0. And that means that they're linearly independent. And so that's kind of, I guess, what we're doing again. And so the example is show the functions f of x equals x, g of x equals x squared, h of x, x plus x cubed are linearly independent on R by showing that the Wronskian of f, g, h does not equal 0 for x in some set of real numbers. So
you should explain this. You should explain this.
Explain this? Okay.
I have
so
a question. I have a question. Do you think we'll be able to make it still 10?
Yeah, of course.
Yeah?
Yeah,
no problem.
Why would that be? This is my job. I do this for a living, and I don't see why that should be a problem.
You won't get paid, okay? Sorry.
Yes, I expect recompense. Okay, recompensation. Okay, so basically what's happening here is we need to show that whatever set it is that these are linearly independent, meaning that we cannot find scalar multiples or any multiples. We can't manipulate them in a way that is constant to get another function in the set. And so as we did in the homework that we were supposed to do last time, but everyone ended up presenting a chapter ahead, you can show this by basically just taking the Wronskian of the functions, which means that, see, the first row has the just plain old f's, and then the second row has the primes of it, right? So derivative of x is 1, derivative of 1 is 0, and then x squared, and derivative of that 2x2, and then same thing for the last line. And basically, remember the n minus 1, you don't want to, okay, yeah, so that's what's happening. So basically, if you can do that and then take the Wronskian of it and get something that's not 0, that means that they're linearly independent. And so that is what we're trying to achieve here. And so do you know how to take the, well, I'll teach you right now, actually, matter of fact. So if you want to take the determinant, go back to the example on page 5. Yeah, so if you want to take the determinant of this thing right here, the first thing you have to do, yes?
Can I do that?
Oh yeah, you're great with this. Go ahead, take it away.
Okay, great. All right, no problem. So guys, I'll be your other TA. Let me just go ahead and open up another share screen so I could show you the work. Yeah, give me 1 second, okay? Gonna open up another slide on a different app. Okay, great. All right, so here we go. Yeah, I think everyone knows how to do this kind of stuff so far, since everyone was doing like work with matrices or whatever. But if we have a 3x3 matrix, I'm pretty sure we know that we have like something that goes like A, B, C, D, E, F, G, H, I. Well, this is at least how you do it in linear algebra. So you take this component or whatever it was. Let's say A is at position like 1, 1, right? Since it's the first row, and then row 1, and then this is row 2, and row 3. All right, and you go down and you got the columns 1, 2, and 3, right? Take that A, and you're gonna multiply it by this little corner here.
Can you zoom in a little bit?
Oh, sorry, no problem.
Yeah,
I was
thanks.
doing on the iPad. My fault. Right. Anyway, so we have the determinant of a 3x3 matrix here, okay? So what you're gonna do is when you have this 3x3 section on your matrix, you're gonna take the entry at like 1, 1, right? Which is A, and then B would be row 1, column 2, following along, and then this one would be 1, 3, which would be C, right? A, B, C. And then in the next row, you'd have row 2, column 1, right? And then you'd have row 2, comma 2, right? 2, 3, and then 3, 1, 3, 2, and 3, 3. Makes sense so far? So in order to take the determinant of this thing, you would take the first component at 1, 1, and then multiply whatever by the determinant of this little section here, right? At the bottom right. So it would be E, F, H, I. If you guys took Calc 3, you're also going to do this. I'm pretty sure you had to have taken it, right? Does anyone know about that?
Yeah, we took that Calc 3. Yeah, I remember.
Yeah. I remember you were there. But
yeah.
Is it a prerequisite for this class?
It is. No, it's a co-requisite.
Oh, okay. All right, yeah. So the rest of you guys, I'm pretty sure you should have learned this by now, or probably learn it. But then to complete the rest of this 3x3 determinant, then you're going to take this middle term, which is the B, which is at position 1, 2, and then you're going to multiply by this guy and this guy, the determinant of this 2, okay? Minus B times the determinant of DF and GI, right? These don't have to be labeled as A, B, C, D, F, G, H, I, you know, but that's just how they taught it to us. And then you're going to add that to the last remaining stuff that you didn't use, which was C, and then this E and H, and you're also going to have this D and G, whatever those are at that position. It's pretty much like you just remember what is where, if you have a photographic memory. All right. Let me just move this over and zoom this out a little bit. Okay. E and G, E and H. And then you compute this. The only way to do this 2x2 matrix now is to multiply these on a diagonal and then subtract it from the multiplication of this. And we know how to solve 2x2 matrices, so this one should be easy. After you get the determinant for this guy, multiply by that, whatever term's in the front. Anyway, that's how you do 3x3 matrices. There's a little rushed explanation, but you know, we'll only have till 10 o'clock. Anyway, David, you may proceed. Let me share it again.
Thank you so much for that aside.
No problem.
That was very enlightening, very
great,
illuminating for us.
Gladly.
Okay.
So that's what's happening here, guys.
Yep. All right. And so as we can see, our solution is not 0, and this means that these functions are all linearly independent. Okay, so the next example is asking us to show that these functions are linearly independent as solutions to that function over there for x is greater than 0. And so it wants you to find a particular solution where y1 equals 2, y prime 1 equals 3, and y double prime 1 equals 4. And so we will use the Wronskian again. And what we're going to do here is simply just list them out. We're going to take their derivatives. See, second line is the first derivative. Third line is the second derivative. And then we're going to do just as we were taught by Greg. And then we see that they are spit out some value which is not 0 for x is greater than 0. So we learn that they're independent solutions. But that's not it. We need to find a particular solution this time. So what we can do here is we can basically sum up these three equations, these three functions, to get a general function y of x. And so we can basically just put
hold on 1
constants in
second.
front.
Thank you. I have no idea. I have lost you. I was talking to myself the whole time.
Oh, that's horrible.
Welcome back, Professor.
How long? For how long you have lost me?
It's been a lot,
15
a very long.
20 minutes, I guess.
20 minutes?
20
20 minutes, 25.
Yeah. 25 something.
We've been doing just fine now.
Right.
We've been
get fun, okay? Get fun.
That's great. So I was talking to myself the whole time.
Wow.
I'm unsure.
Then I was asking, wait, I was any questions? And no answer. I thought, okay, nobody has any question. I was so happy. I said, okay, finally I caught up with my my stuff. Okay, where did you lose me?
We were on page 6, around there.
Oh, 940. So.
Oh my goodness. All right. I guess
20 minutes. Yeah.
Probably didn't record as well. Oh.
No, I was recording actually.
I was recording? Oh, that's great.
The whole time. Mm-hmm.
Oh, you can watch the recording, okay?
I'm not sure if it recorded you though.
Yeah.
I'm not sure if it recorded you.
Oh, recorded you guys maybe.
Yes, I think so.
Yeah, since everyone was left here.
Okay, in any case,
Professor, never mind.
We can keep talking next time, all right? If not, record mine, because it's already 10. We'll talk about next Tuesday, okay?
Yeah.
Okay, all right. Sorry, guys. Oh my goodness, I don't know what's wrong with my internet. My cell phone is perfect.
It's okay. I think we'll be able to catch up next time when you present, Professor.
Okay.
Yeah.
All right. Okay, thank you guys. Keep studying. Okay, great. You guys are doing great. Thank you. Have a good night.
Thank you. Have a great night.
Good night.
Good night.
Thanks. Good night. Good night. Have a good weekend too. Have a good weekend. Have a good night.